Hello, I'm Matt Hargett. Some of you may have gone to my talk at CppCon last year about unit testing. And I just want to start by saying thank you to all the people who either were here last year or saw the video on YouTube or wherever else it is and stuff like that, and sent me lots of nice notes over the last year and asked lots of follow-up questions and stuff like that. I did some remote pair programming with some people who needed some help with their specific code, and I was happy to do that. So thanks to everybody for the warm reception and for reaching out. So maybe some of the new attendees this year will do the same. So this is kind of a part 2 to the talk last year. And if you didn't see the talk last year, that's fine. I'm going to do a speed run through extreme basics. But if you didn't see the talk, the 2014 CppCon talk, whether you're here or you're watching it later on YouTube or whatever, you should probably watch that one first. You can watch it at 1.5 speed or 2x or whatever. You can hear the chipmunks talk about unit testing. But one of the pieces of feedback I got is that the talk last year was a little too high level, focused too much on the selling points of unit testing rather than the technical points of unit testing. So this year we're going to talk about some more technical points of unit testing and some of the deep difficulties with real-world unit testing. So without further ado, there's just a couple of things I'm going to repeat from the talk from last year. The only reason to do unit testing is for a sustainable competitive business advantage. A lot of people come at unit testing or any kind of testing from this kind of warm, happy, fuzzy quality place. Well, the reason quality is important is purely for business reasons, right? So that your customers are happy, so that your developers are working efficiently, so that you have a small QA team, and you can spend, instead of spending $2 million on an extended QA team, you can spend that money on other stuff. So in my experience, unit testing is the most reliable route to a modular / object-oriented design. Some people still have an allergy to the term object-oriented for some reason, probably not at CppCon. But if you don't like that term, you can just say modular. So the reason why is because to do real unit testing, you have to be able to isolate each of the kind of behavioral modules in your system, whether those are classes in a single class in a single CPP file, or a C file that defines some module for whatever it does, that has a single responsibility and complies with other kind of OO principles. Even if you're in C, single responsibility principle still applies at the module level. Or if you don't have the source code, if you're just dealing with, here's a binary.o file, and that's all, and you don't have the source code for it for some reason. Because you have to be able to unit testing, you really have to pull those things apart and get them super isolated so that you can do proper unit testing on them, mock out their collaborators, and do what you have to do to get down each of the kind of deep branches in that module. You basically have to be relatively compliant with just about every object-oriented principle, and here I'm talking about the SOLIDus single responsibility principle, open close principle, list scope substitution principle, et cetera, et cetera. And so unit testing is kind of the proof that you're complying with those things. Because if testing is difficult for some reason, and we'll go through some examples of where testing can be difficult, chances are you have some encapsulation violation or something like that. Then that's the reason why the testing is difficult. And then the last thing is that there's a way to do unit testing in a team or an organization full of teams where it will very quickly start to not pay for itself. And so focusing on the ease of consumption of those tests and the maintenance of those, ongoing maintenance of those tests is key. The way that I think about this is developer kind of user experience. What's the developer experience like? Even if you are a team who's not publishing APIs, I don't mean what's it like to program to that REST API. I mean, what is it like to live and breathe in your code base and work with your team? And there's a whole life cycle here with regards to not just your implementation code, but your test code. Is it easy to read? Is it easy to write? Is it easy to build? And is it easy to debug? And if you do, two of those things, but you don't do the other two, you aren't capturing the whole kind of life cycle of what the developer experience is like. And so if you write a whole lot of tests that nobody can read, tests that are like 5,000 lines long a piece or something like that, or it's hard to write tests because every time you add a test, some other test fails because you have global state or other kinds of transitive problems, or if the tests are really slow to build, so people don't build them. If they don't build them, they can't run them. Or if the tests are hard to debug, the test fails and then it takes like a day in GDB stepping through stuff to figure out what went wrong. Those are all ways that you can get an initial start with unit testing and think you're doing a good job, and then it will fall down as you try to scale it out to the rest of your team if you have a large team, or the rest of your org if you have small teams in a large org. And it's important just to take care of that stuff up front, because if your unit testing is successful and it's finding bugs or it's preventing bugs from being introduced and all that stuff, and people start to have a quick uptake on it, if you aren't ready for that uptake, you could have just been like, hey, unit testing is great, and then it just completely falls over because it doesn't scale. And I ask people to think about these things up front because I like to see unit testing succeed in organizations over the longer term. So here's the agenda. Brief refresher. I'm going to go through it very, very fast. And then I'm going to talk about 4 different areas where in real teams and real projects with real shipping product, 3 or 4 areas where I've seen where it actually required some real engineering kind of problem solving to figure out how do we test this, where it's not just brain dead easy, and it's not the design problems that I talked about in last year's talk. Last year I talked about when implementations are in header files, or you have template classes or other kinds of obstructions that make things difficult to test and how to fix them. I talked about that last year. I'm not going to talk about those this year. But there are some kind of unique problems that I'm happy to share partial solutions or summarized solutions. So the first one is unit testing kernel code, specifically unit testing kernel code, and I'm talking Linux kernel here, but the same kind of thing could apply to QNX or whatever proprietary operating system you happen to be using. Testing that kernel code in userland, so you don't have to inject a unit testing framework into the kernel to get things to work. Mocking standard library functions, basically like how do I mock out receive and send and low-level libc kind of I/O calls. Mocking with singletons and factories, which I touched on one aspect of last year, but the follow-up questions that I got via people sending me messages on LinkedIn or Twitter or whatever and an email illuminated for me that I left out an important deeper detail of that we're going to talk about. And then the last thing is framework customization of assertions or constraints and reporters. There's kind of on the previous slide I talked about the reading, the writing, the what was it? I can't remember. Reading, writing, building, and debugging of unit tests, and there's other kind of some finer points of making sure you have a deployment of a unit testing framework if you're in a large team or in a large org with lots of small teams, that if you're all going to be on the same framework, you should keep in mind so that you don't hit deployment problems, which I'll go into. So, like I did last year, for the multitaskers, I realize in the modern day of conference presentations that people are on their laptops or their tablets or their cyborg implant devices or whatever while I'm talking, and I have made my peace with that. So if you didn't see the talk last year, or you did but you need a refresher anyway, you can go to those URLs and you can read a little bit about Cgreen and read a little bit about mockitopp. Those are the 2 frameworks that my code is going to be, my sample code is going to be in. if you want to just do that in parallel with me talking. Or not. Undivided attention is great too. Remember the good old days? You can just search for YouTube on YouTube for Practical Unit Testing in C++ in the CppCon YouTube channel, and you can find it. Don't watch the video while I'm talking. But that's not the multitasking thing I want you to do. But the link is here, and when I give the guys the presentation and they put it up on the website or whatever they do, that link is right there, so you can just click on it. So here's the refresher. The entry point to unit testing for me in any team or company or whatever is, what was the last major bug that you had? That especially bugs that got deployed to customers or got out into the field somehow, right? Because those are the bugs that got past all of your other safety nets. They got past your QA, your static analysis, your code reviews, your blah, 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 right? So if it got past all of your safety nets, assuming you have a series of safety nets, let's be optimistic and assume that you do, those bugs that get out to the field are so expensive to fix. You have to fix it and then deploy a fix, and if that fix then introduces more problems, then you're in a world of pain. So those are the kinds of pains and costs where it's like, okay, let's introduce unit testing. It's not completely automated, like we have to actually think about the tests that we're writing. People go, well, we don't have time to write tests. And it's like, well, if you don't have time to write tests, but you do have time to do emergency deploys to the field for the customer at 3 o'clock in the morning, I don't understand that. Everybody has their preferences on how they like to spend their time at 3 a.m. I'd rather write a unit test at 3 p.m. than wake up at 3 a.m. to do an emergency debug session on a live piece of hardware. So here's a condensed example from a real product that I worked on. So the bug report says that there's a crash when some device is missing. How do we test regardless of the hardware, right? Because for unit testing, we want to test the code that we're writing in our development environment, right? Not on the board, not on the appliance or whatever. You can test there too, and you should test there too. But the first thing we want to do is make sure that the code that I wrote is what I intended it, does what I intended it to do, not accounting for on the target board, the compiler that you're using is going to have a wrong code bug. Yes, all that does happen, and that's why integration tests and system tests are good, and you should do those too. But for unit level testing, we want to be in the development environment so I can build, run, modify, build, run, modify, build, run, modify in a very, very tight loop. If I have to upload to some embedded device on a 9600 BPS UART, every single time I make a modification, I'm going to batch up my modifications, have more modifications every time I upload the firmware image, which means that there's going to be more mistakes potentially. So when something does go wrong, I have a larger diff to look through, and that gets in the way of me being a productive developer. So how do we test regardless of the hardware? And is it big enough? I think it's big enough for you guys anyway. So here's a small code example regarding PCI devices. And so let's pretend like this is the implementation source file, broadcast.c. The names may have been changed to protect the innocent. So what we want to do is that we want to stub out the collaborators. So how do we find out what those collaborators are? Well, one thing that we know what the function name is. So in our main, we declare that at the top because in a legacy code, in a legacy code base, just pound including one file can sometimes just bring in a whole world of crap of static constructors and macros with weird names and no namespaces and stuff like that. So when I'm unit testing a brand new system, I like to just, here's the function I want. I just want to take the .o that contains that function and include as few header files as I possibly can. So we declare it at the top. If the header files are all fine and you can pan include them, great. But if you can't because they complicate things, then don't. And then I just have an int main. I'm not using a test framework here yet. I just have an int main, and I call get broadcast ID from network, which was the function on the previous page. And I just have it return 0. So I go to compile that, and it says, hey, there's an undefined reference to PCI find device and device read packet. This is what Michael Feathers in his book, Working Effectively with Legacy Code, which I hope they have at the table,
They do.
Excellent. This is what he calls leaning on the compiler or leaning on the toolchain, right? It's just like follow the error messages. And that's great. It can be actually quite idiomatic. And this, anyway, it can be quite idiomatic, which is also tedious potentially depending on how many error messages that you have. But in this case, we have two. It can't find those two things. So I'm going to make another file where I'm going to stub out those things. I'm going to call it PCI mock. So I make a PCI dev struct, and I make a PCI find device, and I'm just going to return null, right? I'm just trying to get it to link before I get it to run, right? And just deal with one thing at a time, right? So, okay, we put our stubs in place, we get it to compile, it links, we go to run it, right? And the bug was that it crashes when the device isn't present. So we expect a crash, right? But is this the right crash? Is this the crash that we actually expected to happen? And what if we need to like stub different values? Like we just made, our implementation of that function, that stub, just return null. But what happens if we need to return non-null or have a series of return values? Like I want to return something good, something good, something good, something bad. So we need something smarter than stubs, which is mocks. So we want to use mocks when we need to have a different return value each time the mock is called. On a per function, if we're talking about C or global functions, or per instance, if we're talking about object instances in C++. We need to do that so we can exercise robust code paths, right? And the background I really come from on this is like parsing binary networking protocols, where especially if someone is trying to attack your protocol stack, they're going to be sending you messed up packets, right? And instead of just sending you like the first packet, like the beginning of the handshake being messed up, the real good bugs are underneath all of that, right? Where it's like, I get so far into the IPsec or the IKE negotiation, and then it's like on packet number 18 into the handshake, I introduce some kind of funky packet that causes a buffer overflow or some other kind of bug. So we want to be able to exercise those robust code paths in these kind of critical systems. And we want to do that without too much maintenance overhead, right? We don't want to have like a different like link time mock. We don't have like mock PCI that returns 1.c, mock PCI that returns 2.c, mock PCI, like that's ridiculous. And it's ridiculous because of the amount of maintenance overhead where if I change the signature of that function, I have to now go edit however many files. So we don't want that to happen. And what would be really swell and nice is if that specification of like return this, return this, return this, return this, that sequence of return values and things were within the scope of the tests so that I could just look in one place at the test and see what's going on. So here's an example using a Cgreen mocks-like syntax, even though we're still just in our main function here. So I'm going to be able to write like expect PCI find device will return null. Expect device get packet will return null. And then I call get broadcast ID from network. So that's cool because now instead of having to go to PCI mock.c and see what does that stub return again? I don't remember. Oh, it returns null. I can just see it right here. And if I want it to return non-null, it's all within the scope of that test. It's all within those two curly braces. And this is one of those things where we're optimizing for readability. For us, for our peers, for whatever. And we want to prove details of a fix, right? So before it was crashing, we don't want it to crash when the device isn't present. Let's say that what we actually expect is that it'll do a print K, a kernel log print, when the device isn't present. So in the second example there, I set my expectations for the collaborators, those two global functions I'm mocking. And then I set an expectation that print K will be called. And in the Cgreen mock parlance, if I set an expectation something will be called and I get out of the test and it wasn't called, that is a failure. Again, I'm going through this very quickly because I did this stuff last year, but I didn't want to like go into this completely cold. So So Cgreen, and some of you may notice, like Cgreen has moved to GitHub, so has mockitopp, the other framework, which has really instigated a lot of activity, which is great. So all the examples are using Cgreen. Cgreen is cross-language between C and C++. It's the exact same framework, the exact same syntax, whether using C or C++. The reason why that was important to me for the projects I was on is because all of those projects had kernel mode components, which were written in C, and then userland components, which were written in C++. And having two different frameworks with completely different syntaxes and completely different semantics between those two parts of the technology stack made the uptake of unit testing very difficult. So Cgreen basically is kind of one framework to rule them all across all of all of those teams. They could all read each other's tests, they could all modify each other's tests, and it was just reduced the kind of barrier to entry there. The other thing is Cgreen, there's no kind of weird code generators in between here. This is just pure C and C++. And there's some macros and stuff, but we try to keep that to a minimum. We try to make sure things are namespaced if you're using C++ so that everything plays really nice. So in Cgreen, we say describe whatever the system under test or the component under test is. And then we have before each and after each. That's a setup and teardown that runs before each test and after each test. And then the tests are phrased like ensure whatever the context is, in this case TCP parser, and then however you want that to read. Reading as English is nice because you can generate documentation from it. We make a TCP parser, and then we assert that parser underscore read. Parser underscore read, when I pass in the legitimate parser and I pass in null, returns null. So assert that parser read when I pass in parser null is null, and then assert that the parser count when I pass in the parser. That's hard to say. When I pass in the parser, that the parser count is 0. So basically, what it's saying is like, oh, if I tell you to parse a read, but I give you an invalid argument, don't increase that parse count. That's the behavior that this test is pinning. So I go to compile that test, I go to run that test, and then it fails saying expected parser count for parser to equal 0, but I got 1 instead, right? The thing that's nice about this, and this is that readability piece of this, is that I don't have to set a breakpoint to see what the return value was. I know what it is. The test runner just told me. And this is like the nice thing versus just using like flat out C-level asserts and stuff like that. And that little round trip there about what is it like for the developer when the test fails is a key part of developer user experience, especially when you're scaling up an engineering team or a development team or bringing in lots of juniors. So Cgreen supplies a mock framework like we talked a little bit about before. And so in the previous test here, wait one second. Nope, never mind. So in this particular thing, what we're doing is that we are going to mock out the function called stream read, and it doesn't have to be here in the test file, right? It just needs to be there at link time so that when the consumer of stream read, when we're linking, it actually gets a stream read symbol to link to. And here, inside of it, we're calling the mock macro of Cgreens. And the mock macro takes in the arguments and the argument names, so it takes in the names and the values using some preprocessor magic, and then returns some value. So we're describing TCP parser, the before each and after each are empty. And we're saying ensure TCP parser stops reading at the end of the stream. So I make a TCP parser. I'm going to set my const end of stream to be -1. And I'm going to say expect stream read. So expect that will be called when the parameter named input is non-null. And then I want you to return end of stream, right? So what it's saying is when stream read gets called, I don't care what the input is as long as it's not null. And when that happens, return end of stream, which in this case is -1, right? And then we call parser.nextChunk. And the implication here is that parser next chunk at some point collaborates with that global function called stream read. and then, right. And then we go to run the test, and it says, I got more calls than expected to stream read. We only gave it the expectation it would get called one time, right? Because if it gets called, and then that returns -1, it shouldn't get called again. You're at the end of the stream. Why are you continuing to, why would you continue to call it? So, so this is an example of, stream read for whatever reason, we wanted to mock it out. Maybe it had I/O in it, or it connected to the network, connected to a database, did something computationally expensive. Who knows? Who cares, right? The main thing that we're testing here is the interaction, right? We're not unit testing stream read here. We're unit testing the TCP parser, and so we're trying to isolate the TCP parser from its real collaborators, because the more real actors that you bring in, the more real collaborators you bring into a test, the harder it's going to be to debug, the wider the surface area that you'll have to debug when something goes wrong. And so by doing these mocks and isolating it this way, we have exactly one file to look in, right? Which is wherever the TCP parser object lives. Our mocks are right here in the test file. We don't have to go anywhere to go look for them or anything like that. So that's link time mocks with global functions. What about actual C++ testing? So there's other mock frameworks, and I want to go into the pros and cons of each of them. But the one that I recommend and use is mockitopp. And basically with mockitopp, what mockitopp ends up doing underneath, which is so really just utterly magical and amazing, is that it creates anonymous classes at runtime based on a pure virtual class that you give it. That's the crux of how it works. So here in this example, do I have a mouse or a laser? Anyway, here in this example, I have a struct stream, and it has a pure virtual method on it called read. And then in my Cgreen test, I make a mock object of stream. And then I tell that mock object of stream to expect a call to the read method on stream, where the parameter being passed to it is a 0, and I want it to return 0. Looking at the syntax, you're like, what's the big deal? Who cares? Yeah, it's a couple lines of code. Go look at the implementation for this. It's really, really neat. Trevor Pounds, who authored mockitopp, did a great job. So then we need to pull out that stream type out of the mock. So we say mockstream.getInstance, and that gives us a stream reference. And then we can pass that into the collaborator. In this case, it's TCP parser. And then we call parser.nextChunk. So these are basically two different examples of the same thing, except in one case, we're mocking a global function, and that's what we have to kind of do our mocks on and insert a mock at link time. Here with C++ and having a pure virtual interface and stuff, we can do that same kind of composition at runtime, right? There's this awesome thing about C++ and objects. So that is as quick as I could reasonably make it refresher on the stuff from last year. So now we're going to get into some deeper topics. And I've hopefully left some time at the end so that you guys can also just poke me in the eye with some really deep, hard questions about the code, your own code that you work on. So unit testing kernel code is difficult because there's obviously ways that you can dynamically load kernel modules that have unit testing frameworks in them and load them and unload them and run them that way. But if something goes wrong, you're going to panic either the VM that you're running in, or your own machine if you're doing it on your live machine and not inside of a VM. But also, you can't use Valgrind. You can't use the various address sanitizers and blah, 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 all the stuff that's built in the Clang and GCC now either. That kind of demands okay, we need to bring that stuff into user land somehow. How do we do that? Because anybody who has tried, and probably a lot of people here know, that if I tried to compile a kernel mode C file, a Linux kernel C file, in userland with the userland compiler, that doesn't work. The kernel has its own idea of certain symbols, certain low-level functions, et cetera, et cetera. So, so they just conflict with the userland libc. So we need to do a couple of things. We need to undefine certain symbols that are in the kernel headers that conflict with libc, whether that's new lib, glibc, whatever, you name it. Redefine certain things before we include those kernel headers so that they don't conflict or so that we can intercept them. We need to supply some link time mocks for some kernel functions that are either macros, and we don't want to define the whole macro right in our compiler command line. Or just inline functions that aren't macros, but they're inline functions inside of the kernel headers that, thank you, that we need to be able to intercept and things like that. And in a few cases, we have to supply a few alternate data structures. And I didn't quite understand why, actually, but it's what we ended up having to do at a company a few years ago to make this work. We also need to use some of the kernel compile flags, but not all of them. And I've listed them here. You need data sections and function sections, but you definitely need to not have the memory model be the kernel memory model. That won't work super great in userland. And I will say that this is kind of fragile, which is maybe a minor understatement. And you may have to tweak your approach with this every time you do a kernel upgrade that changes the headers in any reasonably significant way. Because you're really kind of breaking the encapsulate, like you're really trying to get these kernel headers to do things that they aren't designed to do. And I don't think it's a design problem or an encapsulation problem necessarily on the Linux kernel's part. I'm not trying to disparage the Linux kernel or any other kind of embedded operating system kernel header files or structure or anything like that. I mean, what you're really doing is you're really breaking the encapsulation layers quite purposefully to try to get kernel code to run in a way it was not supposed to. So what does that look like? And I've put the more complete thing up at that GitHub gist. Surprisingly, you do have to undef false and true. Those definitions that are in the Linux kernel header files will conflict with what GCC wants to do with those things, or Clang or whatever wants to do with those things. Undeffing always inline, again, conflict there. Changing some of these functions and some of these structs like fdset, devt, timerT, block count, and all these kinds of things. We're changing the names of those things so we can supply an alternate implementation at link time. Undeffing bool, that's right. It's a little mind-blowing to look at this sometimes. And this is cut off on mine. Oh, no, it's not. Yeah, so various header files have little things that will conflict with glibc. And I'm just going to give a shout out to Alexei, who I worked with at a company a few years ago. The challenge was basically thrown down where it's like, well, why can't you just test kernel stuff in userland? And no one could articulate in detail why. And he sat down for however many days and just figured out this header file has this conflict, this header file has this conflict, this header file has this conflict. And it was super tedious, but at the end he was able to do a presentation where he's like, we're now testing our kernel mode components in userland, and it's saving us this much time for each test run because we won't have to do a bunch of stuff to get our tests into the kernel. So shout out to him. So one thing to note is that we use the preprocessor there to introduce mocks. And that's, you got to do what you got to do. Anybody who saw the talk last year, I said that a lot. You got to do what you got to do. But preprocessor mocks are not ideal, right? And those are also mentioned in the Michael Feathers book, Working Effectively with Legacy Code. And the reason why is because if in my implementation file, if I have an if-def test, then do something else. It's no big deal to be like, okay, well, I'll just, when I'm compiling that implementation module for unit testing purposes, I add the -d test and it's easy in the build and it's easy in whatever, and who cares? Well, the problem with that is that you're now compiling the same code twice. Once for your implementation link, once for your implementation that you're going to link it into your final shipping thing, and once for your test. And for one object file that's small, who cares? But when you when you set that precedent, two things happen. One of which is that you get these weird ass if-defs all throughout a source file that just clutter up the whole file. I don't like that. That's bad news. It impairs readability, et cetera, et cetera. But the other problem, the more kind of operational problem, is that if you're doing that often enough in enough of your source files, you are building everything twice. And if you do this properly, and I'll just be judgmental, properly, if you do things properly and use natural modularity seams at link time, where I can do link time substitution, or at runtime, where I have a pure virtual class or a function pointer and I can do substitution that way, when you use those seams instead, you compile your implementation module once and use that implementation module to link into your shipping code. I love that you're nodding your head, by the way. You can use that same object file to link into your shipping code and link into your unit test harness. And I compiled it once. Right, that's one thing, and even if I'm using CC cache or distcc and other stuff to speed that stuff up, this is just one of those death by 1,000 cuts things that's important to get right the first time. But also, preprocessor mocks are often used when you're kind of hacking around some terrible design problem. And in a legacy system, where it's like, well, we don't have any tests and we're free to change anything, so we don't want to make any design changes to introduce link time seams or runtime seams, you can fall back on preprocessor seams as a way to get some tests in place so that you can refactor it to get better, more modular seams in place. That's cool, but it's not like, oh, yeah, we added some preprocessor seams, there's -d, test blah, 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 or I renamed a whole bunch of functions at the preprocessor level, and now I'm going to enter a bug to go fix it later, and I'm not going to see it for 6 years. Don't do that, because those first tests you write and the way that you do that is going to set the precedent for how people are going to do it in the future. And if the test is successful and finds a bug or prevents a bug or whatever, and people go like, I'm going to copy that test because that's the test that found the bug. If you do a suboptimal job or don't, I don't say that. Basically, if you don't do things right initially, you'll find that the success in unit testing will fall down pretty quickly, because as it goes out to scale across a dozen engineers or a dozen teams or whatever, and everybody starts to do the same crappy stuff, that death by 1,000 cuts builds up. People go, this would never work, and they think it's intrinsic to unit testing. So let's see. In this particular case, we have to use preprocessor seams. There's just no getting around it, because we can't reuse those object files between the userland object file we compiled and the kernel mode object file anyway. We have to compile it twice anyway. So that's why it's more okay, and I don't know of another way to solve it. So what I would say is avoid preprocessor seams in most scenarios. Favor link and runtime mocking, but you got to do what you got to do. Realize that when you use a preprocessor seam to mock stuff, it has this cost associated with it. So next thing is mocking standard lib. So in my experience, typically when you want to do this, it's not to mock malloc necessarily. That's a common gotcha question people ask me, like, how do you mock malloc, smart guy? Well, there's ways to do. I mean, I have an answer. You can. But in my experience, the real world scenarios where you do this is typically with I/O calls, like low level I/O calls, like receive, fopen, fclose, whatever. I want to avoid any I/O in my tests, because any I/O is going to slow everything way down. But also, I want to be able to basically mock or simulate error conditions with those I/O calls, right? Where fopen doesn't succeed or whatever. But I don't want it to go actually touch the real file system, because if I've got tests screwing around with the file system, that's effectively global mutable state. And that's bad news for having tests that run consistently and all that kind of stuff. So, mocking stdlib. So preprocessor injection, that thing that I just said we should try to avoid. It's like, well, you could. And maybe if you're using a compiler that doesn't have the switch I'm about to talk about, excuse me, maybe that's what you end up doing. And there are worse fates, to be sure. So what I would say is favor isolating those system-level interactions and encapsulate those platform specifics into its own module. And anybody who works on a large enough code base that has to run on enough machines, and I know there's a ton of video game developers here, and everybody has their own cross-platform kind of like encapsulation layer and stuff like that, for every major studio anyway. So most people do this already, but if you get all those low-level kind of platform-specific interactions, in this case, platform-specific being POSIX, libce kind of stuff, into its own module, then we can take that one module, that's the only module that calls receive directly, or that calls fopen directly, or that calls, is it flock or lockf? I programmed an HPUX9 a long time ago, and it wasn't POSIX compliant. And so it was flipped one way. Now I can never remember which way it is in actual POSIX. But anyway, all those low-level calls are then in that one module. So we're going to put those tests into their own binary. And once they're in their own binary, we can compile those tests with the flag -no standard lib. So when you use GCC or Clang and you don't specify it to link against anything, it's actually implicitly linking against a set of stuff that you're probably going to use. libc being one of them. Some math stuff being another one, and the networking libraries and stuff like that. So when you specify -no standard lib, you're saying, don't do anything for me. And that means that you may need to, you will need to bring in individual things that you need. And I'm going to show an example of this in a second. And for some compilers, you may also need to disable intrinsics. If you have a weird custom tool chain for a weird custom embedded thing, and they didn't want to make inlines in a header file, and so they made intrinsics that do I/O stuff and not just mathy stuff, you may need to disable intrinsics. I saw that happen one time. So here's our implementation, and here's the test that we want to write. So on the left, we have a socket stream class. It has a method on it called listen that calls receive. On the right-hand side, we have our test, a Cgreen test. We describe socket stream, blah, blah, blah. We want to ensure socket stream calls the platform receive when listening. A very basic test, to be sure. So I make my socket stream, and I say expect receive when socket is non-null. I just care that it's called with a non-null socket. I could do some more checking there, potentially. And then I call socket stream.listen. And just to reiterate one more time, if it gets to the end of that test and receive isn't called, I set the expectation it would be called. If it's not called, the test will fail, and it'll say, hey, this thing that you said an expectation for wasn't called. So what does our receive mock look like, right? So this is what our receive mock looks like. We include syssocket.h. We're still using the same header file under the presumption that the implementation for receive is an inline in the header file, which it's not on the platforms that I have worked on. I include the Cgreen mocks. I use the namespace Cgreen. And I have my own implementation of receive here that calls the Cgreen mock macro and passes in all the arguments and does all that jazz. So then I'm going to, here's a big one. Let's see how this reads. It doesn't look too bad up there. So then I say g++ -no standard lib. I give it the include path to the Cgreen. Cgreen includes. I'm compiling receive mock. I'm compiling my socket test. I'm statically linking against libcgreen.a. I'm compiling a shared library because that's how I do my tests in Cgreen. And I'm going to output that as sockettest.so. And then we get just a shit ton of linker errors as far as the eye can see. And oh my God, put the gun in my mouth now. What am I going to do? Forget testing, forget Cgreen. I hate the universe. Thank you. So and I think I said this last year too, especially when you're working with legacy code and you're like you're kind of leaning on the toolchain, leaning on the compiler, sometimes you will see just the preprocessor or the linker just vomit all over your face. And you're just like, oh my God, how long is it going to take me to fix this? And the Hitchhiker's Guide, don't panic. Right? Sometimes it's the same complaints over and over and over and over and over again, right? So you have to implement 3 mocks and the whole thing goes away, or you have to do one little thing and the whole thing goes away. So in this case, I had to add -lc. There was a bunch of things that Cgreen uses, file stuff, console IO stuff, that I said no standard lib. I told it, don't help me, and it didn't. Right, so I just added -lc to bring the low-level libc functions, which still excludes the networking functions. I would have to add -lnet, so it's still going to call my mock receive. My mock receive at link time is the only receive symbol in town, right? Oops, sorry about that. One other cool thing here is that because we did it this way instead of with the preprocessor like -d receive equals receive mock or whatever. We are reusing that same socket stream object file like I just talked about, which is like what we like to do. It proves the modularity of our design as well as helps keep our build times low. And I'm going to say modularity rules. When you see this stuff work in a real code base, it's like one of the things that still gets me excited about programming, where you just plug different stuff together and it all just works because the interfaces are nice. It's ace. So the next thorny-ish issue, and I touched on Singletons last year, but some people are like, well, what about this scenario? And I realized, oh yeah, that's a common scenario, and it's just one I didn't mention last year. So what some people do with Singletons is that they think the point of the Singleton design pattern, whether you like design patterns or you hate the gang of 4 or whatever, they think it's an excuse to have a globally accessible symbol where they just have to pound include one header file, then access this one instance all over the place, right? But it's really, what it's really supposed to do is to guard against creating more than one instance of whatever that thing is. It's not to get global access to it from anywhere all the time. So for non-trivial singletons that you collaborate with, and what I talked about last year, is that instead of just referring to the global symbol of, I don't know, statistics : instance increment, or arrow increment or whatever you're doing, instead of just referring to that everywhere, you parameterize statistics into the constructor of the class it's being used in, so that your interface advertises its collaborators as much as possible. Generally good practice. Extract a pure virtual base class for that, whatever that singleton class is, like statistics. Change the parameterized version to the abstract, the pure virtual base class. And then guess what? I can mock that pure virtual base class, I can inject it and whatever. But what if you have singletons that are just universally accessed everywhere? And the canonical example of this is a logging system, right? So if it is universally accessed, you don't want to go adding abstract logger star to every single constructor in every single class. That's nonsensical. And as dogmatic as I may seem at times, I'm ultimately pragmatic. But I have had to argue with people to be like, no, we're not going to add that to every constructor. That's silly. So if it's universally accessed, we can still do link time mocking, and that's still modular. It's not runtime substitutability, which is the awesome thing about C++ and objects and stuff. But it still proves the modularity at link time. Link time substitutability is still modularity, and so that's still cool. And so the way to do this is that we have a link time mock that wraps and forwards to mockitopp, so that we can still use mockitopp or gtest or gmock or whatever things. So we can still use those expectations in that syntax. So the common header that we have here for this basic logger, it's a singleton with an instance and a static, and it has 2 methods, void and fatal. And notice that those aren't pure virtual, by the way. So that you could also use this if you're like, I can't make a pure virtual base class for that singleton or for that whatever. I'm going to do link time substitution, even though runtime substitution would hypothetically be better. And then on the right-hand side, we've just got a stub or null implementation of a logger there. So here's where we have a link time mock that wraps mockitopp, right? So we include logger, HPP, that interface, or that header file, which is not pure virtual at all. And we can include the mockitopp mock object thing. We use a namespace, et cetera. So for mockitopp to work, it needs a pure virtual class. But we don't want to mess with the actual logger implementation for some reason, let's say, which is perfectly fine. So I have to make a parallel interface that the actual logger, the real logger, doesn't inherit from. And if that feels weird, it's because it is weird. But if you can't inherit it, you can't change it or whatever, you can still do this. You just have a little bit more duplication, a little bit more maintenance overhead. So I make a mock object logger. I make a mock object for that logger interface that I just made. And so here I am. The next thing is I have a logger instance, which is going to satisfy that header file's declaration, right? That I have a static instance method that returns a const logger star. What I'm then going to do is the implementation methods like info. And I didn't implement fatal here, but it would do the same thing. What those end up doing is that they're calling, they just forward into the mockitopp mock object for that interface, where that interface happens to have the same methods and type signature as the logger class. Wish I had a laser pointer, or that this was a smaller room so I could point.
You did have a mouse earlier.
Did I? I can't see it.
Oh, it's there.
Is it?
Yeah, we can see it.
Oh, okay, now I see it. Yeah, sorry. Yeah, so this line here is what I'm talking about. Note to Microsoft people who are here, the Office thing where it shows the PowerPoint thing where it shows the slides over here as full screen of my notes here. That's really cool, but I'd love to see the mouse cursor as the audience sees it. File a bug or a ticket or whatever at the off. I know the Office team is here somewhere. They're here last year, so a polite feature request. I'm satisfying the link time requirement that logger header file set up, which is that there's an instance method called info. And I'm just forwarding it on to a static instance of a mockitopp mock object. And then the next example, the next topic I have, I'm going to show you how I then program that. So mocking factories. Factories are like singletons, right? They're kind of object creation pattern-y, wibbly-wobbly, timey-wimey type things. So what some people get into is they're like, okay, I'm going to mock my factory, but then that factory has to return mocks. And then those objects that the mock factory returns also have to return mocks. Does it ever end? Is it turtles all the way down? Mock turtles all the way down. I'm here all night. Maybe you have to mock that whole chain when doing deep testing of error handling, maybe. But at the same time, if you have to in your tests, you have to know what that whole chain of collaborators is and exactly this returns this, and that returns that, and that returns that. This is a violation of the law of Demeter. And so, or Demeter? Demeter, thank you. Some people have opinions about this, where they go, law of Demeter is just dot counting or arrow counting, and it's complete bullshit, and who cares? But here's the thing, is that when I have in my tests or in other parts of my code, A, arrow B, arrow C, arrow D, arrow whatever, if I go to change that structure in any way, if I insert some new relationship into the middle of that, I don't have to go through my whole code base and change all of those. It breaks encapsulation is what it comes down to, right? And breaking encapsulation is a nice way to say makes more work for you later that you will hate yourself for. So even though you can mock factories, thank you, and you can return mocks from those factories maybe you don't want to be returning mocks from those. If you get to that point, you probably have some minor design issue where you need to have an adapter of some kind or some kind of wrapping class, which is the thing that you ultimately mock. So poor encapsulation is harder to test. If you're testing and it seems hard or verbose, probably some design issue. Not always, probably. And harder here means a long list of verbose mocks. So I don't think that this is a bad example. I think that this is a practical, real-world example. But I think if you went one level beyond this, I would rethink really hard about what you were doing. So this is another Cgreen type test using a mockitopp PP. So I have a proxy object, and it takes a socket factory. And I forgot to put a get instance in there. It takes a socket factory. And so I make a mock socket factory. I pass it in as a collaborator, adding a .get instance on there if I were smart. And I need that socket factory, reading the name of the test here, ensure proxy logs fatal message when control socket fails after second handshake, right? And these are the fun bugs. These are the fun bugs that come in from the field and you're looking at the code up and you're like, what the hell just happened? Right? It's way deep in the weeds and you're like, well, how would, I don't know, neutrinos, attenuation, whatever, right? The bits get flipped if you're not using ECC RAM. All kinds of stuff can happen. So I'm going to make a mock. Oh, that's right. I have a pointer here. I'm going to make a mock object of socket called working handshake socket. And I have some commented out expectations here where I'm going to set expectations so that those things will return values like they're working OK. And then I have a, can't see it. There it is. I have a broken handshake socket. And I'm going to set some expectations on that so it returns bad data and misbehaves somehow. So then I'm going to tell the, where are we? The mock socket factory, Dr. Seuss in the house, the mock socket factory. I'm going to tell the creation method, where am I? I'm going to tell the creation method when it's called to return first a working handshake socket, first to return a working handshake socket. Second time is called return the working handshake socket again. Whoops. And then the third time, return the broken one, right? And then I'm going to tell the mock logger instance from back here. I'm going to tell that mock logger instance to expect a call to fatal with a standard string that says ouch in handshake 3. And then I call proxy connect, right? So this is an example of I mocked the factory. I mocked the things that the factory returns to a good testing end, but it's not violating law of Demeter, right? We aren't exposing like the whole chain of all of the relationships between all of these objects. And what did I say here? Oh, one thing to think about when writing these kind of expectations is reading the test is one thing, and that is important. But think about if this fails, what does the mock output look like? When the mock expectation fails, like what does that read like? Do I have to, if the immediate thing is it'll look like crap, just set a breakpoint or something like that. Try to think about how you can write these things so that the failures are readable. So the last thing here is deploying a test framework. One of the problems that I've seen in multiple companies, and not just with Cgreen, but also with Gtest and even CppUnit and stuff like that, is that when unit testing starts to get going at scale, each team does customizations, little customizations to the framework. And then so on the build systems, you end up with 20, 30 plus copies of the same framework with a lot of tiny little changes. And if you get your LD library path a little bit wrong or whatever, you're picking up some other team's version of the framework that doesn't have your changes or does, and just becomes kind of a deployment nightmare, just like I guess a DLL hell kind of thing. So in my experience, teams in an org will likely want to be able to customize assertion/constraint/matchers, right? They want to be able to write their own assert equal for their custom object types, for deep comparison of some custom types or whatever. That's pretty common. And they might want to customize the reporters of the output, right? They want to output it in some file format that their custom continuous integration system can slurp up, or whatever else. So one piece of advice, and there's no code for this, but it's a general general piece of advice, pick a framework that allows you to customize those things without a recompile. We talked a lot about modularity, and last year I said unit testability is modularity, is object orientation, et cetera, et cetera. Pick a framework that embodies those values so that when people are using the framework, they won't learn bad things. So there's the links again to Cgreen and mockitopp PP. If you're going to consume those things, I would highly recommend, or gtest for that matter, or gmock if they keep their tests passing. Maybe they do, I don't know. I highly recommend tracking those repositories and building from source in your build. Thank you. Thank you guys very much. I hope this was useful and filled some gaps for you guys. Again, I'm going to whore out my music. My music's at themakingofthemakingOf.com, and it's on Tidal, iTunes, Amazon, Google Play, and Spotify. That's my Twitter handle. If you have questions for me, you can tweet at me. You can contact me via email. You can contact me via LinkedIn, stuff like that. The next talks that are coming up after this talk, Const Expert Introduction is in this room. Practical Lock-Free Programming is in the feeder room, which I guess is downstairs. Haskell Design Patterns C++ are in room 407. C++ in the audio industry is in room 406. And Expression Templates is in room 403. I'm out of time, so if you have any questions, come up to me after the thing, and I'll be glad to answer them for you. Thank you, guys. Thank you.